Well, today we're going to talk about distributed loads on a beam in section 4.9. Well, what we have been doing in the last couple of sections here is trying to come up with a model that is simpler than the real-life situation, a simplified model. And real-life situations are often pretty complicated, and it's very helpful for us to come up with a simplified way of looking at it to help us understand it and also to help us do the math. So let's look at the traffic light situation over here. We got a couple of lights that are mounted to this horizontal member, which is mounted to this vertical member. We can model those lights as point masses. In other words, we're just going to say that the weight is coming straight down. That's pretty easy to see because they are small compared to the rest of it, and even though the weight is distributed along the length, we can model it in this direction as point mass going straight down. How about this crane here? We've done this crane a little bit. Over here on the left hand side we have that weight over there, and we're going to model it as a point. This one is going over this way, but we're still going to model it as a point. And again, that might make some sense because they're distributed over some distance, but their weight can be assumed to be concentrated at a point. Over here on the right hand side we have this load, which is clearly not a point mass. However, because the tensions are going up here and right here, we can say that the entire weight is concentrated right there, so that when it pulls down it acts as a point right like that. On this side, of course, this is distributed across its whole length. It does have a center of gravity, and what we can do is, because this is distributed and because we know where the center of gravity is, we will just assume that all of the weight acts through the center of gravity. And that's kind of our approach as we're going to go forward. Let's look at this this other lift kind of thing over here. Clearly the man up here has some weight. He is not a point mass, but we're going to model him as a point mass acting down through his center of gravity. We're going to say that this part here has some distributed force, but we're going to model it as a point mass coming straight down. This beam over here is just a little bit different. And this is that it has a center of gravity of the beam, and you can see because the center of gravity is only 10 feet from this side and 20 feet from this side, that the center of gravity is not in the middle. In other words, it is not a uniformly distributed load. It is a non-uniform load. However, it still does have a center of gravity, so we can model this as a point that is coming straight down from its center of gravity. Well, what we're doing here is this is an application of the simplification techniques that we have been doing. And instead of having distributed loads, we're going to model them as point loads. So let's look at this load of bricks on this beam, on this board. You could expect that there's maybe some weight associated with those beams and that there will be some effect at A and B. A and B are the mounting points or the supports. If we could find out how much the bricks weighed, we could model it as a point load acting through its center of gravity, separated by a distance d from one of the points. We'll call that point A. And if we did that, we could say that the weight here times this distance is going to have, or the weight consider that weight applied at that distance will have the same effect at A and B. So we're going to simplify this to say that the weight acts through, or that the load will act through the center of gravity. And that means the sum of the forces before is going to be equal to the resultant afterward. The effect that we're going to find is that the moment caused by the individual bricks about any point is going to be equal to the same as the sum of those weights acting at that distance. And that's kind of what we're saying here. The sum of the moments before is going to be equal to the mg, or the weight, acting at a distance d afterward. Now let's see what happens if we add an additional load to one side. Let's say we still have our original load, and now we're going to add another load of bricks here. I think we could probably guess that there's going to be a center of gravity of that load, and obviously there's still the existing center of gravity of this first load. If we add those two loads together, we should be able to get a resultant. And then the effect at A and B is going to be equal to the resultant times this new distance d3. And that's what we're approaching here, is we're trying to find the resultant of all of the loads and then the distance at which it acts from a reference point so that the external effects are the same. So distributed loads act through their centers of gravity, and so we need to find out how much the load weighs. The weight is going to be the mass times gravity, and this is something that perhaps we've done a little bit in this class, not so much, but we're going to really start using the weight versus the mass as we're going forward. So let's say that in the metric system, or the SI units, the weight will be expressed as a force, which is newtons, and that's going to be mass times gravity. In the English system, the weight will be expressed in pounds, and that will be the mass, and the mass in the English system is slugs, and then the acceleration of gravity is 32.2 feet per second squared. It's very important that you keep that last significant digit in all of your calculations, 9.81 and 32.2. Even though it's small, I want you to keep that in there. Now the load in English system again are already expressed, if they're already expressed in pounds, then don't multiply them by 9.81 or 32.2 or divide by 9.81 or 32.2. This is a really common error for students at this stage. We're not quite used to working with pounds and masses, or weights and masses, I guess, in the English system. The metric system is a little bit easier, I believe. So we're going to do it this way. We're going to distribute it. We're going to model distributed forces as a shape in our modeling, and we're going to understand that the weight is proportional to the area of the shape. The weight will act through the center of gravity in a real world, but in our models, we're going to act through the centroid of our modeled shape. Next thing is make sure that the weight always acts down from the centroid. In other words, keep this, don't rotate any pictures or anything like that. Look at it straight on as if it were a real life situation, and weight always acts down. Alright, here are some shapes that we are going to consider. Mostly we're going to be dealing with rectangles and right triangles. We also can model shapes as a function of x. However, that would be using some calculus, which we're actually not technically doing in this course. So this will be an optional thing that will, our optional consideration. So mostly we're going to be dealing with with rectangles and triangles. So what we have to do is find out the area of the shape to find out how much it weighs, find the centroid to find out where the weight acts, and then the centroid will be the geometric center of the shape. For a rectangle, it's pretty easy. It's just going to be the area is just going to be the base times the height. So if you know what the base is and the height, we know that the area is base times height. The centroid of that will be acting straight through that. For example, let's say that we have a distributed force in our book. We'll say that it is 50 newtons per meter. If it's 5 meters long, well, 50 newtons per meter will be represented as the height. So if we want to find the total weight of this, it will say that it would be 50 newtons per meter times 5, which would be 250 newtons. And it would act through the centroid of that distributed shape, which would be right there in the middle. So the weight will be 250 newtons, and it'd be acting right there. For triangles, we're not going to do this integration, but you can refer to the book. There's an example in there to convince you that the centroid of a right triangle will be 2/3 from the, I'll call this the skinny side, and 1/3 from the fat side. From the bottom, this will be 1/3 from the long side and 2/3 from the top, if you will. So you'll hear me use 1/3, 2/3 quite a bit as we're going forward. We're mostly going to deal with right triangles. If you find yourself working with an isosceles triangle, then the centroid in the vertical direction will be 1/3 from the bottom, if you will, or 1/3 of the height, and then the centroid in the x direction will be 1/2. If you have a other kind of triangle, then here's our little formula. This is in the back of the book, and you'll find that the area is still equal to 1/2 BH, which was kind of nice when we're dealing with this, and you can find out where the centroid of that right triangle is using this formula. So maybe I didn't quite mention this before or back here, but the area of a triangle, that's what I should have done. The area of a right triangle is 1/2 BH, and the centroid would be 2/3 from the skinny side or the small side. Here's a real-life situation which can be modeled as two uniformly distributed loads. For example, we got some books here on a shelf. They're obviously not uniformly distributed, but we model it as a uniformly distributed load as a rectangle. And so we can say that because these books over here are pretty much all the same, we're going to say that those are modeled as 2 pounds per foot. Over here, these are taller ones, and we're going to say that those are modeled at 3.5 pounds per foot. What that means is that for every foot you go in this direction, you add another 2 pounds. Starting in this, and from here, you say for every foot that you go in this direction, you add another 3.5 pounds for the total weight. So we'll just use that concept as we're moving forward. Okay, so here's our first problem. This is a distributed load that is modeled. It's a real-life situation, I assume, and we're going to model it like this. So what we want to do is understand that there's a resultant force associated with this, and that at the end, the resultant force placed at a particular distance will have the same effect as what this distributed load does. So let's go ahead and draw our forces here and our resultant. Well, first let's draw the resultant. We're going to say that this is the end here. We're going to say that this can be modeled as a resultant separated by some distance from point A, and that's what the problem is asking for, some distance from point A. And the way we're going to approach that is to try to find the resultant of each one of these distributed loads. So let's look at the left one over here. Let's say that it has a resultant coming down here. I'll call this R1. And again, because we're measuring this from point A, we're going to say that this has a distance x1 from point A. The next resultant is going to be in the middle of this distributed load, so I'll call this R2. And it's going to be separated distance x2 from there. Then the last one over here is R3, and its separated distance, let me erase a little bit of that, it's going to be separated to distance x3 from point A. Okay, I hope that you can see all those distances. First of all, let's find out what R1 is. So let's choose this, R1. This is the resultant force, and what we have is this distributed load over here is modeled as a rectangle. So the resultant R1 is going to be equal to the base times the height. So the base is equal to 1.5 meters, and the height is 6 kilonewtons per meter. And so we're going to say that that is going to be 1.5, the base, times 6. So that's going to be equal to 9 kilonewtons. What is the distance x1? x1 is going to be from we're going to model this as acting through the centroid of that rectangle. And so this distance right here is going to be halfway through that. So x1 is going to be equal to 0.75 meters. All right, how about R2? R2 is the base times the height, and the base is 3 meters. The height is 9, so that gives us R2 is equal to 3 times 9, which is equal to 27 kilonewtons. X2 is going to be halfway of the point of the 3. In other words, this is 3 meters. And so this distance is halfway there. So that would be 1.5 meters from point A. So that'd be 1.5. Let's try R3. R3 has, the base would be 1.5. The height is 3 kilonewton per meter. So that's going to be 1.5 times 3 equal to 4.5 kilonewtons. And X3, you have to consider that it has to go 3 meters first, and then the centroid acts right there, which is half of that 1.5, so it'll be 3 plus 0.75. So X3 is 3.75 meters. Okay, what is the resultant? The resultant is pretty easy. The resultant is equal to the sum of the forces. In this case, they're all in the y direction, so let's just go ahead and put those in there. 9 plus 27 plus 4.5. And that's going to be equal to a total of sorry, I lost my picture over here on my other side. It'd be 40.5, and that's kilonewtons. And what is the effect? This is all the before. And let's move this up here just a little bit and see if we can find out the moment before, and that needs to be the moment afterward. Okay, so before, moment about A caused by the distributed forces is going to be equal to R1 times X1, and that's going to be going in the positive direction. In other words, it's going in the counterclockwise direction. However, R2 is going in the negative direction, times X2 minus R3 times X3. So let's go ahead and write all those in there. R1 is going to be 9 times 0.75 minus 27 times 1.5 minus 4.5 times 3.75, and the total moment is going to be equal to negative 50.63 kilonewton meters. So again, this is the moments caused by these loads before we do the simplification. This one's going in this direction, this one's going in this direction, clearly that one's going in that direction. Alright, let's look at what the after scenario might be. Let me just again move that out just a little bit. So the after scenario is going to be that the moment about A is still going to be equal to negative 50.63. However, that is going to be equal to the resultant times D. I know what the resultant is equal to. That is equal to 40.5, and the distance D has to be computed. So we can solve that, and the D is equal to 1.25 meters. Okay, that's kind of the way that works. We're going to call this distance D, going forward, we're going to call this distance D x bar. And what x bar is the distance from our reference point to the centroid of our total situation.